So far in this workshop, we've looked at how we can use linear mixed effects models to analyse data from multiple sites to help describe hydroecological relationships. And we've also looked at how we can use the HE Toolkit to assemble the data, the hydrological and ecological data ready for analysis. However, before we jump in and actually start fitting models to the data, it's still important to explore the data and visualize it. And in this tutorial, we're going to look at a couple of functions from the HE Toolkit, which allow us to judge how useful or suitable the data will be for building a model. Specifically, we're going to look at the plot site PCA function and the plot range of flows function. Now, when we choose to bring together monitoring data from several different monitoring locations and use that to calibrate a single hydroecological model, we need to make sure that those sites are ecologically and hydrologically similar, and therefore we can expect those sites to behave in a similar way or respond similarly to flows. Here we are going to take the site level environmental data that we obtained using the import env function and perform a principal components analysis, which is a way of summarizing a large number of environmental variables down to a smaller number of uncorrelated axes. This provides a really simple and visual way of mapping out sites to identify how similar or dissimilar they are with respect to particular environmental features. And from this, we can identify any sites which might be fundamentally different, potential outliers from our data set. So in this example, we've got a set of variables here: altitude, slope, width and depth, and then 4 substrate composition variables. We use the plot site PCA function, feeding that environmental data set in as the first argument, then confirming which variables within that data set we wish to perform the PCA analysis on. We can then choose, we've got a couple of options at the end which control how the outputs are visualized. What the PCA does is produces a biplot like this, whereby the sites, each here represented by their site ID, are mapped in a 2-dimensional space. The 2 axes, which we call the first and second principal components, are a product of the individual environmental variables that we fed into the analysis. The first principal component, as you can see at the bottom of the slide, explains 36% of the variation in those original 8 environmental variables, and the second axis explains around 23%. So together, the PCA has taken 8 variables and boiled them down to 2 variables, which represent together around 60% of the variation. This provides a nice straightforward way of summarising how these sites compare to each other in terms of their environmental characteristics. The blue lines on the plot are eigenvectors. They show how each of the component or input environmental variables correlates with our principal components. The direction of the arrow points in the direction of the positive correlation, and the longer the arrow, the stronger that correlation is. These eigenvectors allow us to interpret the axes in our plot. So, for example, the first principal component is positively correlated with the percentage of boulders and cobbles, and negatively correlated with the proportion of sand, silt, clay, and pebbles and gravel. So we can broadly interpret this as a substrate gradient, with sites on the left representing having finer substrates and sites on the right having coarser substrates. Then if we look at the vertical dimension, the second principal component, we see that that's positively correlated with slope and altitude and negatively correlated with width and depth. We can therefore interpret that second vertical axis as a gradient, with sites at the bottom that being larger, deeper watercourses, typically in lowland environments, and towards the top we have smaller watercourses at higher altitudes with steeper gradients. The closer together any 2 sites are, the more similar they are in their environmental characteristics. And what we're looking for here is to try and identify whether, for example, our sites might cluster together into 2 or more distinct groups, or whether there are any individual sites which might be potential outliers, which are fundamentally different from the rest of our data set. In this example here, we can see that, at least in relative terms, we have a mix of sites, some being having relatively fine substrates on large watercourses, and others being on smaller watercourses with coarser substrates. But there's no one site which really stands out as an outlier, and neither is there any obvious grouping. So this plot sites PCA function is a useful precursor to confirm whether we want to keep all the sites in our calibration dataset or whether we wish to exclude any on the basis that they are atypical. The other thing we can do with the HE toolkit is to explore how well our biological sample data covers the range of historical flow conditions. When we're modelling the effect of flow history on a biological receptor, we ideally want our sampling data to cover both wetter and drier periods, ideally over several different cycles as we go back in time. If our data does span a wide range of hydrological conditions, then first of all that gives us a better chance of being able to detect a hydroecological relationship because we have a wider hydrological gradient over which we can make observations of our biological community. And secondly, it means that if we want to use our model to simulate or predict ecological responses under different flow scenarios, then we're less likely to have to extrapolate beyond the boundaries of our calibration dataset. Here we have an illustration of the plot range of flows function, which we can use to visualize how comprehensively our biology sample data spans that range of historical flow conditions. We first of all prepare the data using the join-HE function that we discussed in the earlier tutorials. We use join type equals add biology to take a table of flow statistics and then join in the biology sample data, the actual metric scores, where those samples exist. You can see the table on the slide there provides a simple illustration, and the final column basically flags whether or not we have a biology sample for each time period. That provides the input to the range of flows function. We then specify two flow statistics from our table. So in this case, we've chosen the Q95 and the Q10 statistics, both of which are standardized and for the lag 0 time period. We also identify the column which contains our biological metric. So this basically flags whether or not we have a sample associated with each time period. And then we have a wrap by argument. If we set that to null, then we get an output which visualizes our entire data set for all of the sites, or we can choose to wrap by the biology site ID, which gives us a more detailed breakdown of coverage for each individual site. The output from the function is shown on the right-hand side. It's simply a scatter plot with our two chosen flow variables representing the horizontal and the vertical axes. Each of the points on that plot is a particular time period for which we've calculated flow statistics. You'll see that there's two coloured polygons. The outer grey polygon is describes the full range of flow conditions across all sites and all time periods. The orange polygon within it describes the range of flow conditions which are associated with a biological sample record. In this particular instance, you can see that the orange polygon encapsulates, it covers the vast majority of the points on our scatter plot. This indicates that in our data set as a whole, across all sites, our biological data span both higher than normal and lower than normal flow conditions with respect to both Q95 and Q10. We therefore have observations of our biological community under almost the full range of flow conditions. And that gives us confidence that this data set is suitable for us to use to calibrate a hydroecological model. The small number of black points which fall outside of the orange polygon are A, very infrequent, and B, they represent extremely high, unusually high flow conditions at these locations. And it's only under those extremely high flow conditions that we have an absence of biology data. So we can be therefore confident that we have a good data set for modelling and that we can use any calibrated model to make predictions under quite a wide range of flow conditions.